Hi everyone, welcome back. So this is another data analysis video, and I am still covering probability distributions. So in the previous two videos, I talked about the normal distribution, the Gaussian distribution, and I kind of demonstrate how to simulate or generate random data uh, using Python that follows a normal distribution. We then looked at how to visualize that so we could see the shape of the distribution, obtain parameters from it. And then in the last video, I kind of moved on to demonstrate how we could simulate multiple variables that all follow a random distribution, and you could stitch them all together to create some sort of pandas data frame. Should you want to then run some sort of statistical analysis or hypothesis test on it, all simulated data, all made up, but may be useful for educational purposes. As I've said before, data is inherently noisy, and it's often difficult to get data sets to use for demonstration educational purposes that match exactly what you're trying to demonstrate, or are very good for illustrating some particular statistical analysis. So it can be useful to sort of simulate your own data sets, give the variables names, and kind of use them for illustration purposes. So what I'm going to do in this video is carrying on from that. I'm still talking about the normal distribution. I'm going to generate a data for a new variable that also follows a normal distribution. What I'll do is I'll set a seed before doing this, and that will allow the kind of pseudo-random results that are generated, so the variable that's generated, to be replicated. So anyone else who runs the same code will get the same results essentially. And then I'll explore the data in various ways through visualizations, distribution fitting to get the actual parameter, using the actual parameters from the data that's been generated. And then I'll use the probability distribution function, the cumulative distribution function, the percentage point function, to find different probabilities and values for given outcomes. Okay, so to start with, I'm going to run this code cell here. So I'm planting a random seed using the NumPy set seed method. So what this will do is ensure that results are replicable. And here I'm using a seed of 0, and I could have chosen any number, so this is completely arbitrary that I've chosen 0. So I'm using np.random.seed, and I'm passing the value of 0. And if anyone else does the same thing, they'll get the same results. They simulate data like this. Could have picked any value, 12, 24, anything, doesn't matter. And then I'm going to create a new object, generate the data, which is I'm going to save as an object called x_ran, so x variable, random data essentially. I'm going to use the numpy np.random.normal method, so I'm asking it to simulate data that follows a normal distribution. And I'm specifying here I want a mean, so the log of 0, a mean of 0, and a standard deviation, this scale argument, of 1. Okay, and I'm asking for 1,000 observations, 1,000 participants, 1,000 data points, however you want to think of it. So the data I'm going to create here is going to very closely follow a standard normal distribution with a mean of 0 and a standard deviation of 1. So having done that, we can then plot this variable in using Seaborn. So we use sns.hisplot, and we'll pass the actual object as the thing we want to plot. And you can see there straight away using a histogram that it's selected, automatically selected. That, remember, I think the data we've generated here will be floating point decimals, so they're continuous numbers on a real line. But the histograms plotted them as kind of discrete values. So Seaborn's kind of selected the bin width that kind of it thinks gives us the best visual representation essentially. And you can see here that this data with 1,000 data points is already looking fairly kind of bell-shaped, fairly normally distributed. It's not perfect, but this is kind of a finite data set essentially. 1,000 data points is quite a bit, but it's not a huge amount really. We can add a KDE line by setting the parameter KDE equals true. So this will give us a kernel density estimator of the shape of the distribution. And if I run this cell, we can see here that it's largely normally shaped. So this KDE soft line, this line plot here, it gives us a visual way to assess the distribution shape and any skew and a long tail at the end of the distribution or the other, or whether it's particularly peaked or flat, so kurtosis. But in this case, it looks, you can see from that KDA, that kernel density estimator, that it's fairly normally shaped. Okay, so that's our data that we're going to use. Let's do some distribution fitting. Okay, so here what I'm going to do is use the SciPy stats function to obtain the parameters for our data. So this will return the actual mean and standard deviation for this xrand object variable that we created. So I'm importing stats from SciPy, and then I'm specifying loc, comma scale is stats.norm.fit xrand. So I'm basically telling it to fit the distribution using and return the mean and standard deviation from our data variable. So if we do that, what you can see here is the two values returned are the mean and the standard deviation. So that we've got a mean of negative 0.0452, etc. So if it was negative 0.05, if we round that up to 2 decimal places. So that's our mean. So we asked for a mean of 0. It's not exactly 0, but it's very close. Yeah, and remember there's noise in this because it's randomly simulated data. Okay, and then likewise for the standard deviation. We've got a standard deviation of 0.987. So that's very close to the standard deviation of 1 that we specified when we generated this data. So the parameters are not perfect. They're not a perfect match for the values we specified of 0 and 1, but they're very close. And there's always going to be some error, some noise, because our data is based on a sample of a finite size. Okay, so let's now look at the probability density function. I think I called it the probability distribution function earlier, but it's the probability density function. So the PDF represents the relative likelihood that a variable takes a specific value. Okay, so first of all, I'm going to create a vector of values on the x-axis. We can then use some of those values to assess their probability. Okay, and a PDF is kind of appropriate here because the data we've simulated will be decimal, so it'll be continuous values. And PDF's the kind of distribution function that is used when you have continuous value data. So it's infinitely divisible, essentially. If we just had discrete values, measure it as measurements for our variables, so values could only take on specific observations could only take on specific values, such as 1, 2, 3, 4, 5, like integers, then we'd use a probability mass function instead of a PMF instead of a PDF. What I'm going to do here is create a vector of values on the x-axis, and then we'll use these values to assess their probability. So I've called this object xvals, and I'm basically using the NumPy linspace method, giving it values to start and stop at, and asking it to kind of generate 100 numbers. And then we can create the PDF from these xvals that we've just kind of created, this vector of values of 100 values we've just created for the x-axis. We can create the PDF from these, specifying that we want to use the mean and standard deviation from our simulated data. So if you remember above, we fitted xrand of a normal distribution, and we created these objects loc and scale, which represent our exact, from our simulated data, our exact mean and standard deviation. So what I'm doing here is create an object called PDF. I'm using to do that. I'm using stats.norm.pdf. We're passing this vector of 100 x values, and we're saying the mean and standard deviation for this is going to be these above, the 0.045, negative 0.045, and a standard deviation of 0.987. Okay, so let's plot that and see what it looks like using the matplotlib plt.plot function. So notice here what I'm doing is I'm passing xvals, PDF, and the PDF object as arguments here. So that's what a PDF, a probability density function, looks like. And you can see here we're kind of, the peak of it is around about 0. So we've got a mean of 0, and we will have a standard deviation of roughly about 1. Okay. So what we've done here is plotted a standard normal distribution line for that simulated data using the parameters of the simulated data. So using the exact mean and standard deviation from our xrand object we created. So this PDF plot shows us the probability of getting certain values on the x-axis. So we can see the most frequent or most likely value is kind of 0 here. If we read 0 off the x-axis, and this has a probability, if we look across, this has a probability of kind of just above, maybe about 0.4, yeah, so 40% chance of a value of 0. And we can also see that, if we look at plus or minus 3 standard deviations, these values are kind of much rarer, so they're kind of the probability of getting a value of of x that's about minus 3 is really close to 0, or x that's at plus 3 is really close to 0. Okay, so that's the PDF kind of useful way to it was a kind of useful way to look and see roughly what values of x, what the probability of getting those values are. When you have a continuous kind of distribution like this, it's kind of there is no real mass, so it's tricky. It's tricky generally to say an exact value has a given probability. So what you often find is you have to specify between two x values. So and then sum that up. So what's the probability of a score between -1 and 0? And you'd have to kind of sum up the area under the curve within that space. Okay. All right, so the cumulative distribution function, the CDF, this tells us the probability that a given x has values lower than a specific value. So the CDF is basically the cumulative sum, or the integral of the PDF. Okay, yeah, so it's monotonically increasing, which means it always increases as the scale increases in x. And it has a range between 0 and 1. Okay, so what I'm going to do here is create another object called CDF. I'm going to use stats.norm.cdf this time for cumulative distribution function, and we're going to again pass in this xvals and our loc and scale from our simulated xrand data. So let's run that and then plot the CDF, and we'll get an idea of this kind of S shape that it has for this particular data. So the CDF plot here can be used to tell us the probability of getting a certain value of x or lower. For example, if we read the value of 2 from the x-axis, if we follow that up here, say, we can see that where it meets the black CDF line, this indicates that probability that's 2 is really, really close. The probability very close to 1, probably around 0.98, or about 98% chance of getting a score of 2 or lower, essentially, on this particular, for this variable, on this particular scale. So that's quite useful. We'll come back to this in a second, but let's look at the percentage point function as well. So the percent point function, the PPF, is the reverse application of the CDF. So here we've kind of said, given this x value, what's the probability of this x value or lower? Yeah. With the PPF, we're going to do it going in the reverse. If in this case, if with the PPF, if we took a specific probability on the y-axis, we could use the PPF to tell us what value that represents on the x-axis. Okay, so to use the PPF, we first need to create a vector of linearly spaced values from the CDF. So I'm going to call this, I'm creating a new object called CDF underscore. Okay, and I'm going to use np.linspace again. I'm going to go start from 0 to 1 and ask for 1,000. So I'm creating a vector of 1,000 data points between 0 and 1. And then what I'm going to do is I'm going to create a new object called x underscore, and this time I'm going to obtain the PPF using the CDF on this CDF underscore object as an argument. So I'm going to use stats.norm.ppf, pass in CDF underscore this vector as an argument, and telling it, for these 1,000 data points, we're going to use the mean and the standard deviation from our actual random data we generated. Okay, so if we plot the PPF, we get the same plot as above, like the cumulative density distribution function. The only difference is we've used the PPF to plot the x-axis correspondingly. So if you notice here, the x values, the values on the x-axis have changed. Essentially, they're wider because we asked, because we've used the PPF essentially. And what we can do here is given a specific probability, we can kind of work in reverse with the PPF. Given a specific probability, like what value of x is there, or is there an 80% or lower? Is there an 80% chance of finding? So we come across here and then down, we'd probably find that's about 0.5. There's an 80% chance of a value of 0.5 or lower, essentially. So we're working in reverse compared to the CDF. Okay, so we can use the CDF and PPF to obtain values, specific values and probabilities. So having obtained the CDF and the PPF for the data, we can now investigate how they can be used to obtain values or probabilities. So, for example, what is the probability that the variable x takes values of 1 or lower, essentially? So to obtain this, we can simply create an object using the stats.norm.cdf method and pass in a single value of 1, if this was what we're interested in knowing about, as an argument rather than a vector as we did previously. So if you notice, I'm creating a new object CDF underscore 1. I'm using stats.norm.cdf. Previously, what we did was we passed in a vector as our first argument, which was that kind of vector of this. Yeah, if I go above, it's this one, wasn't it? This x values vector, and then we specified the locus scale to match our random data. What I'm doing here is we're using the same locus scale, but I'm just kind of passing in one value essentially, and not a vector of numbers. And now what this will do here is return a specific value, a specific probability. So 0.855, 0.86 if we round that up. So what this is doing is it's telling us that there's about an 86% probability that someone has a score of 1 or below on the x variable, whatever our random data is measuring. Yeah. Okay. And we can visualize this as well. So what I'll do is I create another plot here of the CDF, but I'll add a horizontal and vertical line at the value 1, sort of highlighting 1 and its associated probability. So we kind of create that. All I've done here is added a little bit of extra V lines, vertical line and horizontal line. And you can see there these kind of blue dashed lines. So x value of 1, we're able to read that off. It returns a probability of about 0.86. Okay. So similarly, we can do that. We can work in reverse with the percentage point function, the percent point function. So what I'll do now is use the PPF to assess what value of x is not exceeded 99% of the time, say. So similar to the above, we're going to, with this time, going to use the PPF, pass an argument of 0.99 to represent the probability of interest. So here I'm creating a new object, x underscore 99, using stats.norm.ppf this time. And whereas we just passed that one value of 1 when we use the CDF, above here we're going to pass an actual probability 0.99. We're still going to use the mean and standard deviation from our random data. Okay, so what this will do will return a value of x essentially. So this is telling us that 99% of the values in the x variable do not exceed the value 2.25. So 2.25 or lower covers 99% of the values within our random sample of data. Okay, and we can do the same as above. We could I'll create a plot that shows those horizontal and vertical lines as well. And there you can see that. So this time we're kind of reading in reverse. If we went from 0.99 here on the y-axis across and read that down, that returns a value, difficult to see on this scale, but it returns a value of 2.25 on the x-axis. Okay, so that was kind of just an example of how to simulate a variable, investigate it using the probability density function, the cumulative distribution function, and the percentage point function. So the cumulative distribution function and the percentage point function are quite useful. If we use the CDF, we can kind of look at what's the probability of a given value or lower. If we use the percentage point function, what we can do is, given a probability, what value does that relate to? So if we have a probability of 99%, what's the associated x value in our data set with that? Okay, so hopefully this was useful. I think in the next video I will kind of provide another example of simulating data, how you can simulate data frames that contain more than just one variable. And after that I'll move on to some other probability distributions. Okay, hopefully this was interesting and useful. Thank you for watching and listening.